So it is now time to act and to use the model, since the model is used in scenarios, in certain functions, as an instrument. So far we have been considering 12 different topics in our module. The last 2 topics have been already elements of the third part of the lecture. Now we continue with methods for model utilization. This is mainly oriented on the kind of the instrument being of models. That means a model has a function, it plays this function in scenarios and is for this reason used as an instrument. We use a wide set of methods. This wide set is similar to any kind of engineering, especially also to systems engineering. Since the function determines the kind of the model we are going to utilize, we also have to investigate how the instrument properties influence the model utility. The utility can be defined on the basis of the triple use: usefulness, usability, and usage. For this reason we introduce now elementary deployment, paradigmatic deployment, model utilization methods, instrument properties, scenarios, model checking. We use service models to show how it can be applied. We might have time to consider design science, and especially the rigor cycle in design science, and the deep model and the matrix synthesis. First of all, let's start with the instrument being of models. What is an instrument? Instruments have a long history in mankind. We are using a lot of instruments, languages, as well as also models. An instrument is simply a device that requires skills for proper use in a given scenario. As such, it is a means whereby something is achieved, performed, or furthered, one used by another as a means or aid, one designed for precision work, and the means whereby some act is accomplished for achieving an effect. An instrument can have several functions in scenarios. The quality of the instrument determines, of course, its utility. That means the usage and the usability and the usefulness. Okay, with an instrument we cannot claim that anything in the model is true. I claim that models must and should be useful. A model, however, brings a number of background, a number of deep model properties. That means biases, beliefs, paradigms, postulates, the culture, theories, assumption, the hidden agenda. It has also maybe a language. That means in this case the language matters and the concepts that are used are important. We have to consider the school of thought, the thought style, the pattern and the common sense that are somehow incorporated into a model and somehow determine how useful the model could be as an instrument in the scenario. We have also guidelines, practices, training, experience that are incorporated into the model. We have a scope, a focus, an orientation, restrictions and idealizations that are incorporated into the model. And of course we have also some kind of observed reality and some kind of augmented reality that comes with the usage of a model in some scenario. That means in this case we should consider the readiness of models, and typically instruments bring all those their internal tacit knowledge with them. We can consider or reconsider the old romp developed by Bernhard, where we have to distinguish origin, cargo, the instrument, and the results of the application of the instrument, as well as the model being. The origin has typically a cargo. The origin is somehow reflected by an instrument. That means the instrument is an instrument of something. Furthermore, we have also results that are anticipated. So in this case, we have also an instrument that is considered or judged as a model. That means in this case we can determine the model being. Maybe we should first consider the reflection between origins and cargo and instruments and results, and then the acceptance as a model used for obtaining results. Let us first consider the first four parts. We have the cargo, we have the instrument, we have the origin and the result of the instrument utilization. In the case of learning situations, we could have the cargo of theories, learners, and the learning situations reflect somehow the learner's worlds and the theory worlds. And then we use an explanation instrumentarium to enhance the learner world. In another scenario or another application, we could think of we are using models for system analysis. In this case, they are system analysis instruments. And in this case, we use informative models for systems, environments, and analysis tools to reflect the system, the environment, and the requirements. And we want to have an insight into the system behaviors. It means we would like to have a performance forecast, and we would like to see the bottlenecks. In a similar way, we could do it also now for the model being part of this romp. For instance, in our database area, we are interested in data structuring, in a proper description of the data structure. Then in this case, we would like to have an instrument that is nothing else, let's say, than a conceptual object relational schema. Finally, we would like to have a conceptual domain situation schema that reflects what is known about the data structure, especially and given by the domain situation models and the concept spaces. In this case, we would like to have a descriptive conceptual model of the domain situations models with some viewpoints. Okay, the same we could have also for prescriptive models of the domain situation. In this case, we use the object relational schema and object relational view schemata for developing the logical database dictionary. That means in this case we have again the model being this based on some stereotype of the kinds of models we consider. This is nothing else as using another representation of the model, as we have done in the model house. You have the background based on the basis and the grounding. You have development methods, and you have utilization methods that typically go into the deep model. And we have to consider the context, the community of practice, of course, the artifacts or origins represented in this case, and some kind of goal, purpose, function, or in general profile. And the whole model being is based on the usage of the model in some utilization scenarios, and maybe in a number of utilization scenarios. In this case we have a spectrum, or maybe even usage spectra. The model has in this case again to play a certain role. Okay, that means in this case the model is something like an instrumentation we have been gaining. We improve or enhance our abilities to something with the origins according to the model function. Of course, we don't want to have the best possible instrument. We want to have only the best model, in our case, for handling the function in the given scenario. That means we have some kind of restriction for the precise precision and for the properties of the model. The instrument usage is also some kind of common tacit knowledge. And of course we want to reach the level of a master craftsman or a journeyman. And for this reason we want to have a really proper professional usage that goes far beyond the garage. That means we have maybe a workshop organization and infrastructure. Instrument usage means also to be able to control, to trace, to diagnose what is done. And we need a proper instrumentation, and the model is in this case used as an instrument of action. That means in this case we have directly instrument biases. First of all, we have a model obstinacy, as we already considered for demography models. This is a restricting factor of the instrument usage. We would like to have a professional model utilization, maybe based on some standardized and stereotyped approaches. We would like to use some tolerance and precision and recall and fallout of the methods. We would like to have some kind of safety and security of the utilization method so that we can be sure that nothing happens in a wrong way. Of course, we are oriented on a model deployment only for the function for which the model has been developed. Any site utilization must be somehow have a viability. Maybe we can use one-shot models as the initial version. We would like to have also a skilled use of models. That means in this case we need to have a proper understanding of the field of modeling and a proper training. Instruments must be maintained. For this reason we have to maintain the model in order to use it really in a proper way as an instrument. We have quite a lot of changes that can happen. We should have also a function check of the model and the elements. We should be able to diagnose, to control, to evaluate, to track, to trace the success of the model utilization. We should be able to organize a better handling of the model, and especially maybe an improvement or sharpening or hardening of the model. Models should have maybe some proper evolution, and for this reason we would have also something like a model retirement. And maybe we have to develop a concept of maintainability, and we have to document and surveying the model application. In this case, we base our usage of models on our skills to use the instrument. We need to have abilities to perform effective and efficient model utilization acts in a given scenario or spectra. We should be able to judge on that. That means it should be observable. We need to manage it in the proper form. We need to have some kind of informative model for quick survey. That means in this case we are using anyway a model suite. Of course, skills are based on the education we got, and we would like to have anything beyond a layman or apprentice. Maybe we should head towards the level of a master craftsman, or maybe at least a journeyman. Okay, that means in this case we have to have an economic way of instrument usage methods. That would be, in this case, of course, thousands of methods we could have, or maybe we can stereotype the model utilization. That would be pretty nice to have such kind of stereotyping. In this case we could handle it in a much better form. That means in this case we might start with elementary deployment and elementary utilization. In this case we go with deployment pattern. We might have somehow a stereotyped deep model inside our models, so we know how to handle these things. We might have also a methods canon. That means we know the rules and the methods in our instrumentarium pretty well. We might have inherent capabilities of the model. We might have a proper deployment discourse. We know how we can use a model in an efficient way, what kind of representation, operation and so on we have in our mind. We know how the capacity and the potential is somehow given in this scenario. That means we go now for elementary deployment based on coordination among various modes within a model suite. We should understand in which way the model is really stable and plastic. That means we know the model universality, especially at the level of the model background. We know how our reason to use a model is really proper, what kind of invariance of the grounding and basis we have there. We know the invariance and grounding. We can articulate every facet in the model structure in a proper way. And we have maybe some regulations of the model components that are not entirely commensurate with the grounding. In this case, we know how to develop things furthermore. What is missing for skill deployment, we can enhance. We have practical limitations, so we can modify. We have proper justification, so we can preserve. We maybe have a practical futility, so we can replace. And that means in this case we have also regulations for reinforcement and expanding, maybe scope and position of the model. We can delimit domain and functions and revise the deep model. Models as deputies have also, in this case, their specific properties. They are representing, reflecting something by something. That could be something that represents the something. Could be, of course, an artifact. It could also be our thoughts. That is the same as we have here with the three, let's say, model stuffs. The model here is a model of that model. The model here is somehow depicted by the painter using some kind of tools. So having these tools, we can directly properly reflect what we can see there. The same would be here, that we have maybe something like a specific form of model structures coming with the concepts. That goes back to design science. In design science we have a relevance cycle. That means in this case we know what is relevant, what should be represented. We have a modeling cycle. That could be, for instance, the sculptor's view. And we have a rigor cycle. That is nothing else in this case as the hidden or the properly used sketchbook to handle the model usage. That means in this case we are again using some kind of stereotypes to have some kind of repeatable modeling scenarios. This leads directly to an observation that goes back to Morrison and Morgan. Models are used as mediating instruments. Of course, a model exists on their own. For this reason, we have some kind of autonomy. The model might function in various scenarios and comes also in a variety of forms. The model for investigation represents either some aspect of the world or some aspect of our theories about it. We can learn from building the model and from manipulating it. The model functions not just as a means of intervention, but also as a means of representation. The model is usually circumscribed, and very often several models will be required to apply these general principles to a number of different cases. Models are a mixture of some experimental and empirical elements and pieces of a bunch of theories. Models can be used as a tool for theory construction. Models can also involve stories and objects which could form the basis of modeling decisions. Models are also functions, or models have functions outside their theories. Models can be built on guidelines. Models can be used for design and intervention. Models can represent the world and the theory at a distinct level. Models have also a representative and investigative role. And we can learn how to place, how to learn in a world of models. And models enable us to learn about the problem we have to solve, about the functions the model plays in the given scenarios. So far, we are often using some kind of quantitative data. In this case, we have maybe some proxy source that can be observed. We might be interested in proxy concepts. We might use some kind of quantitative sources in this case, map them to quantitative concepts, and then derive proxy concepts. That would be based, let's say, on a theory offer that could be used for explaining a theory request. We would like to have something like, in qualitative theory-oriented research, something like supporting sources reflected by theoretical concepts and be based or integrated into theories. However, we have to have a means how to integrate this stuff. I will show now that the mediating function is the missing bridge among these parts in our diagram. Theory offers are widely used. Sometimes they are called middle range theories. They lie between the hypothesis space and somehow are used to develop a unified holistic theory. A theory offers nothing else as we take parts and pieces from different theories and use them in a proper way in an integrated form. We already considered that a theory is a systematical structure of broad scope conceived by humans' imagination that encompasses a family of empirical laws regarding regularities existing in objects and events, both observed and positioned. That means in this case we might use now our understanding that a theory offer maybe is somehow considering the theories behind on the basis of some cutouts. That means in this case we might use models to represent what is observable in the quantitative world and what can be considered in our qualitative world. Okay, then in this case we would have a situation that is the following one. Typically we have a situation, and the situation can be represented by quantitative conceptions if we are able to do such. We will see in most situations we are not able to do such. We go directly to the observational sources, have some quantitative concepts, use some theory offer that could be again represented by a quantitative theory. That means we would like to have something like combined quantitative concepts, and in this case represent what is given at the real micro level by, let's say, our investigation that leads at least to a result. That means in this case we can meet the challenge to derive quantitative concepts and to develop a quantitative theory. Okay, then in this case we would have now, based on our investigative reasoning, some kind of quantitative reasoning, and we could represent the whole thing by models. In this case we are using modeling with model concepts, and we develop a model that is somehow reflecting the quantitative theory and the theory offer. What is inside the micro level is, however, often not really possible to understand. For this reason, we start still with the observations and the sources we have, with the proxies we have in this case. That means in this case, you could say, okay, fine, we can put now the model and the model concepts between quantitative concepts and qualitative concepts or theoretical concepts. In this case, we have now the model as a mediating means in the sense of Morrison-Morgan. And this is the way how we do in general data science or data exploring science. We use our data and we reflect these data later by concepts and use models as a mediator between the two. That means in this case we have nothing else as a situation and sources, compiled sources that result maybe in some kind of qualitative theory and reflect what we have for quantitative theories by models and model concepts. Okay, this will directly lead to some challenges for model-based reasoning. You can use some kind of big data characterization for considering the properties we need to consider. Of course, models can be really large. Models can change. You have a variety of models for different purposes, for different communities, for different contexts, for different backgrounds. You need to have some kind of dependability and, of course, some, let's say, quality assessment and assurement. The value is often, in this case, implicit. Viability of models despite authorities, so you can be sure that you are not biased by the authorities. You have variations, you have views of models, you have a vision, you have a movement, any kind of V you can put here as challenges. I think the most important are the dark red ones: veracity, viability, and different views to handle in a sophisticated, integrated form. Let's consider an example. Let's say we would like to develop a software service. In this case, we know the basis and the background of our systems, our environments. We know, let's say, some kind of sources for the technology, and we are looking for a service that is really properly usable, that reflects the purpose. We have a portfolio for the service as the origin, and we have some kind of context and maybe also a community of practice. That means in this case we could apply the W*H framework for service description. Let's think that we have described our service in this way. Now we would like to use this service specification description in a way that we know which properties, which kind of goodies we get. Okay, we can, let's say, use the workflow behind the service realization and separate different phases. We have a planning for the service. In this case, of course, we widely use our background. We know in this case, or we have to know very properly, the application cases, the function of the service in applications, and of course to know what kind of business rules, portfolio, business deployment we have to handle there. The rest is less important. If we go now for building the service, then in this case we consider, of course, our application cases. We have to have the proper methods for that. we have to consider also what is the basis. The grounding, the deployment is not as important in this phase. Of course, we use our knowledge about the context and the community of practice for constructing the service, for orchestrating, or maybe for choreography. If we go now for the next phase, to use the service, then of course we have to have a proper bundle of methods that we can use the service. In this case, we of course target on a proper support for the application cases, and we consider the service within the functions the service has to play within the business deployment. If you go now further, then we can say, fine, we would like to evolve the service. In this case, we accept whatever has been given already in the background, and we use our methods for development and the methods for applying the service for proper deployment of the service. That means in this case, we have already a number of methods for the utilization in that case, evolving the service especially, maybe without migration and revision of the given service. That leads us directly to description of some utilization stories and scenarios. We might have a very large variety for many function models, and of course we would like to have some kind of systematics. Okay, which functions we have? Using our stereotypes, our special stereotypes of models, then we have to consider 4 different kinds of functions. One is the reflection function, the other one is the engineering function, the sense-making functions, and maybe the social life functions. And then we have a pretty large set of different functions. Oh my goodness. If we count properly, then we have maybe more than 30 different scenarios to consider. Should we develop for each of these scenarios, for each of these functions, a special set of methods? That would be not the right way. For this reason, I would like to use our stereotyping, what we have been introduced in the first part of this lecture, for developing somehow scenarios that can be considered as generic scenarios. That can be refined to the given scenario. For instance, we have been already introducing a story space for the development utilization, like this one. For, let's say, the case of search, then in this case, we have, with the story space, already the ability to refine the service, to derive the proper pattern, to derive the ETL search basis, and of course to repair, to somehow modify, to maintain the given search space for, let's say, search stories. We already introduced 7 different stories, so in this case we might have our own, let's say, way how to specify and to refine the scenarios. It means we come back now, this large set, this variety of functions is not a problem as long as we are using generic scenarios with generic functions that can be refined in a proper way. That would enable us also to consider different model usages together. A model typically can be used, for instance, for description, later for explanation, then for predictions, then for control, later for invention. That means a model has, in this case, something like a journey. It might, at a certain moment of time in a given situation, not be a model. It is only what has been used in the past. Or it might become a model at a later stage. That means we can also reflect now the journey of a model. And in this case we have something like what we call the epos of a model, or the Odysseus of a model. That is maybe far more general than the journey of a model. The model has a utility, it can be used as a production model, it can be used as a workshop model, it can be later used as a post model, then as an illustration and exhibition object, and later for demonstrative or representation models. That means you have something like a mini story that can be again described by our W star H framework. Okay, now we have our, let's say, little Mar rump here, maybe only a part of that. We have the model being that is somehow given by the model category and the specifics of these categories. We have to have tools in support of modeling, and we have to have some kind of enablers for integrating the environment. Now we can consider the application space in a different form. We have a task space. We would like to solve some problems that would have a cause that are necessary to solve, and we are forced to solve that. That is somehow reflecting the origin that must be supported by a proper instrument. And then we use application scenarios and functions and determine what is the reason that this is now considered to be a model. And then we use for the results nothing else as a delivery space where we give all what we have gained from the instrument usage and then maybe solve the problems we have been observing in the task space. That means in this case we have some kind of application space with utilization of models that function in a given set of scenarios. That is a bit maybe too general. Maybe we should consider special cases. Let's go for a special case. Heart models, human heart models, that is a little bit outside our computer science, but still supportable. We have a good number of human heart models. We have empirical models, we have muscle wolf models, we have maybe heart cycle volume pressure models that can be somehow represented. I will go to this representation a little bit more in detail. We have physiological models, we have layered biochemical models, that is a large which is developed by a large community of human heart researchers. We can also consider the human heart as a combustion engine. That means we have a good number of those. Let's go for number 3, heart cycle volume pressure models as a circuit. The typical way how human heart is observed is such kind of electrocardiogram circuit. You have some kind of phase where the muscle is, the volume is increasing, the muscle is strengthening. Then you have some kind of valve opening. Then you have again another cycle, and you can observe these 4 points here as the main parts for what can be done by the EKG. So it can be also represented by some kind of Vickers diagrams. Or you can think, okay, that is nothing else as a pump, sucking and forcing. Let's see, in this way, given by a technical thing. We can also represent this cycle by an electrical analogy model, as Harvey does. Okay, let's go for Harvey's representation. We would like to represent the potential and capacity of the pump volume valve model. So in this case we have a behavior space, and we would like to know what is a, let's say, causing heart insufficiency. In this case we would have maybe some influence of substances, we have the heart potential, we have good and bad substances, and we would like now to know what is the reason that our human heart is insufficient. In this case we are using as the origin already heart models and volume pressure models. And we would like to have at the end some kind of behavior diagram so that we can reason which substances, which parameters have which effect. That means in this case we would like to have some kind of behavior traces that say these are the main influencers. We have, like we do use in synergetics, control parameters and slave parameters, and we would like to have methods for influencing the human heart capacity. Then in this case we use in Harvey the electrical circuit model. And there you find this 4 valves system can be explained by an electrical circuit, and in this case we have the model being of this electrical circuit instrument based on our thoughts that we would like to investigate and explain what is the reason, what is causing some kind of insufficiency. That means in this case we have some hypothesis and we would like to detect the dependencies. That means in this case our scenario is based on the behavior space, is hoping for behavior traces, and we would like to know what is the reason for which kind of behavior based on this modeling mold we are using here. A similar thing could be done, let's say, for experiment-oriented investigation. We have something like a theory, develop models on the theory. We can now use these models for experimenting. The experiments again are evaluated against the scientific model, so that we have to maybe to revise, to modify or to replace parts and pieces in our theory. In general, we are for this reason applying to test hypotheses or to collect statistics, and we get a feedback for our theory based on our situation. And we measure and somehow have a means to express what is the physical situation. That looks again like our human heart approach. We can also use models in education. I took here, and this is in German, sorry for that, a nice picture developed by Andreas Kopp for representing how the Voyager sons are somehow evolving depending on which systems they are approaching in astrophysics. We can also use models for brainstorming. We took it again from the MMM compendium based on a paper written by Allard and Richter for brainstorming and for ordering our thoughts. We can use it also for manufacturing. Here you have the description of the golden head, how the golden head has been made. Or here you have a model that represents how a combustion machine is working. Or maybe you are using later anything that has been developed for counting as a model how these counting machines have been working in the first half of our century. I mean, in this case we have again a number of scenarios that we could use in this case. Okay, let's now go for utilization methods. We would like to have a skilled model deployment, really at the master or craftsman or the journeyman level, beyond the level of an apprentice or layman. In this case we have now a spectrum of methods to consider. We have deployment methods, we have behavioral methods, we have investigation methods, we have sense-making methods, we have agreement and purification methods, and we have explanation methods. That is already represented in our model house at the beginning of this lecture. All these methods look like specific methods, but they can be given in a general form. Using for solving a problem is nothing else as, after application of the model, after getting the result of the instrument application, we can have now a solution of the given problem. That is a typical way how we also construct our systems in software systems engineering. That means in this case we have a bundle, in this case of 6 so far different kinds of methods that can be used in a very specific form and can be directly refined to the given kind of model, to the given application, and to the given function especially. In this case we can use some kind of reasoning frames. The classical frame is the deduction frame. In reality, however, if we want to model something that is somehow given on a number of examples, we are using induction. That comes with positivism, and let's say the main representatives of that are Aristotle, Heidegger, Newton. You can have here a very large number. You can also use abduction to have some reasoning back from the problem to the cause. That goes back to Platon, to Kant, to Einstein. That in this case you have these reasoning frames. They have been quite nice applying in their, let's say, specific theories. Model-based reasoning is pretty rich. I put here a mind map to explain what it means. You have some maybe hypothetical techniques, you have some reasoning techniques that are applicable. You can have specific reasoning techniques like, let's say, proxy-based reasoning, or let's say reasoning on the model, let's say, as an instrument. Model-based reasoning is of course based on, let's say, some observations on some data, on some description of the application case. You typically use model suites in order to know that the models are properly associated, and you can use one model in a model suite instead of using the whole model suite. You have also comprehension, limitations, calculi for reasoning that depend on the scenario. In model-based reasoning, it should be revisable. The model as a process, starting with a suite of generic models. So in this case you have a number of approaches to handle somehow in model-based reasoning. If I use something coming from Egyptology, then I say, okay, fine, I have maybe the old starting point, let's say. I have some reference figures that are used later for second reference figures. And so in this case I would like to know what is the meaning of the figure. For this reason I can now claim what is maybe the hypothetical figure that is later used, and I can control these figures. That means in this case I have something like some kind of retrospective hypothetical reasoning. Okay, let's go back to computer science. What we would like to have is some kind of abstraction facility. Abstraction can be based on 4 different ways how to represent it. It could be the general part, the particular part, the specific part, and the concrete part. In this case you have something like an abstraction layer and an abstraction hierarchy that you can use. And you have maybe some kind of modeling principles in this case. That is one of the general methods that is also leading our stereotypes of methods and the specific refinement of these generic models. A typical way of modeling is also modeling on, or a typical application of modeling, is hypothetical and investigative modeling. You consider different assumptions and you would like to know what is in this case the result if you change the values for parameters, or if you change maybe also the macro parameters of the model, how the model is constructed. That could be also combined with abductive reasoning from the problem to the cause. You could also have some kind of assumptions incorporated, maybe with a possible world conclusion, with assertions that are supporting a number of hypotheses, and maybe you have the way to have some kind of evidence against the hypothesis or supporting the hypothesis, so that you can test the consequences these evidences have depending on what kind of hypothesis you would like to consider. Another kind is exploratory, or I would call it consolidative modeling. Consolidative modeling is nothing else as you use a model as a surrogate for a system. So you can use a model instead of a part of the system, and the model behaves as you would like to have the system behaves. In a different way, you can use exploratory modeling that explores the world depending on which of the hypotheses is correct. In this case, you have again a number of methods. Identify an ensemble of plausible models, identify the range of outputs, identify the relationship between modeling assumptions and modeling output, find assumptions, and identify predictions. Exploratory modeling has a number of problems and opportunities. You should not treat an exploratory model as it would be a consolidative model. You should not focus too much on parts of the problems for which consolidative models are possible. The good side, however, is it could be used as an argument for some options for a policy, for instance, to apply, or it could be used as a communication device or as a bookkeeping device. Again, a model has its advantages and its disadvantages. That means in this case we have something like situation, conceptions, and theories we use. That means in this case we have something like what forces us, what supports us, and what kind of representation you would have. I was putting this picture in the setting of archaeological research. That means in this case you use models as empiric reasoning instruments in an investigation scenario. And you have, of course, a number of concepts that you could say, okay, fine, at what time, at what site, at what settlement, which houses or housing has been used, which kind of ideology you have, and whether it is specific for the Neolithic time. Similarly would be if you use models for statistical computing and decision making. In this case, you have to consider the classical computer science problem again. Garbage in means garbage out. That means if a model should support political decision making, then you might have a means to use mathematical models as long as you have a proper data set. In this case, you can then use mathematical statistical methods, for instance Bayesian reasoning or meta-modeling. You have maybe to consider a number of inputs, the computational core and the computed outputs. You might use also some kind of, let's say, programming support, for instance based on R, that is a pretty nice language for statistical computing. But again, be careful. If you have only garbage data, then you will never get anything else than garbage outputs. Another way of reasoning method is causal reasoning. In this case, you apply a specific variant of inductive reasoning. You can also use justification-backed truth maintenance systems with a number of assertions and justifications. In this case, you can try to reflect causal relationships among the events. You have methods for agreement, difference, concomitant, variation, and residues. You can use associations to reason forward or to reason backward. In this case, you have something like a triple: environment, justifications, and results. And then you use some kind of hypothetical reasoning, and maybe something like maybe logical reasoning based on modus tollens. That means if you know that I is not true and you have H implies I, then you can conclude that H is not true. Another kind that is not very well investigated so far is network reasoning. But this is a natural way how human reasons. We reasons on our network of neurons that have a lot of different connections, maybe in a certain time or at a certain time. And in this case you have nodes. If you have edges, you have maybe the representation for at least a network of labels, so that then you can distinguish the meaning of nodes and edges. And then you might have some kind of computational reasoning based on queries. These queries can be formulated in network reasoning mainly on subgraphs that can be somehow embedded into the network. And in this case, of course, you have maybe a simple, coherent, complete, and relevant explanation. This would lead directly to evidence-based proxy modeling and reasoning. The models represent only acceptable possibilities. The models in this case are proxy-driven. The model represents what has been observed, not what is false. And of course, the more proxies that are considered, the richer the models are, the more accurate is the reflection on the world. And you have maybe some pragmatic reasoning schemata. That is similar to what we are using in mental models. Again, in mental models you have some kind of reasoning about acceptable possibilities, which are consistent with the premises and the knowledge gained so far. What makes them intrinsically uncertain because they mirror only some properties that they represent. That means in this case we again are based on our observations, on our realized observations, and in this case we have maybe some kind of proxy-driven reasoning. And of course, again, we represent only what has been observed and not what is not observable, what is false, what is not existing. That means in this case we are representing only what is really observable and has been observed. Of course, in this case, our mental models have the problem that they are based on our observations, on our perceptions of the observations. So they must not be really completely true. But you have some pragmatic reasoning schemata. This can be extended to these different reasoning methods to causal behaviouristic reasoning. This is another thing than system-oriented reasoning. In system-oriented reasoning you have at least a system model as an origin, and you consider this system model for the instrument. Typically, system-oriented reasoning is based on multi-layered systems with inner and outer components, with observable components and non-observable components, with some kind of non-deterministic, non-linear or random behavior models. And you might have goals and maybe laws. And in this case it goes back to Kant, Bertalanffy, Deppert, Kralemann, to Kurt Lewin, to Parsons and to Ernst Mayr, like it is used in the philosophy of the biology. A typical way how we apply our models for somehow analyzing our systems is model checking. In this case you have an upper part that is somehow development of models for requirements. You formalize them, of models on systems you would like to consider. And in this case you apply now model checking procedures in order to know whether our requirements are satisfied, or if they are violated you would like to have a counterexample, maybe based on some kind of simulation facility, so that you can have a description of the errors. That depends of course which kind of requirements you consider. Model checking is typically considering only the performance, dependability and performability, and you have a methods canon for the properties for the systematic checking at least. We can also use the reflective turn for qualitative theories. You go with some kind of speculative concepts with ideas, thoughts, suppositions, hypotheses. You model them and then you get some kind of current world model. That is a generalization of middle range theory. And then you use your observable data world to get an augmented model world, and for this reason an augmented concept world of ideas, thoughts and theories. That means in this case you go down from qualitative reasoning to model reasoning to quantitative reasoning, again back to model reasoning, and again back to qualitative reasoning. This agenda is also a typical way how you do, let's say, data mining or data analysis, or how you apply in a systematic way at least some data mining in the maybe crisp data management approach or mould. That means in this case you try to have some kind of proper way of reasoning mechanisms, of applying these mechanisms to the model base. Okay, this leads again back to the different kinds of logical approaches. You have deduction, you have abduction, you have induction. In induction you say, okay fine, I have observed a number of properties, I have observed in a subset of situations another properties, and then you can conclude whenever I observe one property I can also observe the other property, if it is even applicable. Inductive reasoning can be generalized to Bayesian, Occam's razor and Solomonov induction. In this case you go with making an observation, forming a hypothesis that explains the observation, and you conduct an experiment so that you will test the hypothesis. If it's confirmed, then provisionally accept the hypothesis, else you can revise the hypothesis. That means in this case we have again some kind of inductive reasoning techniques that starts with given a set of knowledge and belief, given models and data, so then you cannot somehow derive a contradiction for the knowledge and the model according to the data, and then you would like to discover some kind of explanation that allows you to say which kind of data are, together with the knowledge and the model, somehow derivable, but the model, the knowledge and the data don't allow to derive alpha. That means alpha is somehow a better means, and you can incorporate alpha into the model, and in this case you have a good explanation for the data. You can extend it also to all AI-like reasoning methods for non-monotonic reasoning. You can enhance it by deep learning with model suites or with respective reasoning techniques. Okay, for utilization acts I would like to refer you to lecture 15 on engineering. For this reason, no longer explanation. For quality, please go also for chapter 15 or 16. Yeah, what we have now reached is we know what is proper instrument utilization, and of course that influences model utility, and in this case we know now how our methods somehow can be properly used and which methods don't lead to a believable result. So in this case we have now a number of goodies. We considered model utilization is of course a kernel for the instrument being of a model, and is of course somehow the basis for the model being of anything. The next lecture will be now using models for, let's say, programmings. So in this case we are maybe on the path of industrial software development based on developing a model and computing the corresponding program directly from the model. That means in this case we would like to consider modeling as programming, model-based development, modeling as programming. That means in this case we would like to have some kind of automatic way. That would already a good benefit of modeling. So in this case we can use models instead of programs. Thank you. This will now pass to the next lecture, and this will be nothing else as the low principle of the internet. Let others do the work. Let others develop the model instead of programming. Thank you.